Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about green energy. Now, that's a phrase I'm sure you've all heard about. It's a idea that's important for the future of the planet. And I'd like to try to use this episode of What's the Big Idea to try to connect the ideas about energy that we're learning about in Physics 107 to these broader societal issues. So let's dig in. So, what do all three images on this slide have in common, and why are they referred to as green energy? Well, I would say uh, the main thing that they have in common that's important is that none of them emit carbon dioxide or other uh, greenhouse gases when they're producing power. So, wind turbines, uh, solar panels, and hydroelectric dams are all ways of generating electricity that doesn't require the burning of fossil fuels and doesn't therefore emit carbon dioxide or other dangerous greenhouse gases into the atmosphere. So they all look wonderful, but they each have some limitations. So let's talk about those important limitations. Well, for a long time, the limitations with solar and wind power were a lot of it was economic. It was just too expensive to build solar panels or to make efficient windmills to compete with burning fossil fuels. Coal was very cheap, and it was hard to compete just on economic terms. But that's actually changed pretty dramatically in recent years. The price of solar panels and the cost of generating electricity via the wind power has fallen dramatically, and it is becoming cost competitive with burning fossil fuels. But there's an important remaining limitation, and that is that the sun doesn't always shine and the wind doesn't always blow. So, if you're going to run the electrical grid with these sorts of power sources, you're going to have to deal with the fact that they are intermittent. Hydroelectric power doesn't quite suffer from the problem of being intermittent in the same way that solar and wind power is, but it does suffer from the fact that there are a limited number of geographical places in the world that have enough flowing water and other sort of the topography is well suited to generating electricity via hydroelectric power. And if you happen to live in Canada, you're very fortunate. Canada has abundant hydroelectric power and a relatively small population. So they derive a lot of their electrical energy from hydroelectric power. But it doesn't quite, at least in the form that's being shown here, it doesn't quite work to supply a country like the United States. We don't have enough places where we could build hydroelectric uh, power to satisfy the demands of our large population. So, what to do? What to do? Well, there are some promising ideas of how to deal with the limitations of these three forms of green energy. So, energy, as you know, can exist in different forms, and windmills, for example, wind turbines are, as you saw in a previous screencast, are devices that take energy that's in the form of kinetic energy of moving air or wind and convert it directly into electrical energy. Solar panels convert energy in the form of sunlight into electrical energy, and hydroelectric is similar um, to a windmill in the sense that it's converting the kinetic energy of moving water directly into electrical energy by running a generator, much the way a windmill does. So to deal with the intermittency problem, you need some way of taking the energy, say, of the blowing wind, and instead of converting it directly into electrical energy, can you take that energy and store it somehow so that you can use it later? So on a windy day, you have a lot of energy that you're collecting. Can you temporarily store it? And then use it on a day when it's not windy? Or similarly with solar energy, is there a scheme for taking the energy in the sunlight that you don't need on that you have an abundance of on the sunny day and temporarily storing it? And one idea, which we already see actually being played out in this picture, is of course, before this water was moving, it was stored in this reservoir, and this reservoir is a higher elevation than the base of the hydroelectric plant. And it's really the difference in potential energy of the water when it's up in the reservoir compared to where it's down here that we're taking advantage of. So you can think of the reservoir as a giant sort of energy storage tank. It's storing energy in the form of potential energy, and then you open up the dam gates and let the water flow, and the uh, potential energy gets converted into kinetic energy of moving water, and then that kinetic energy of moving water can get converted into electrical energy by the generator. But as we said, a problem with this idea of hydroelectric power is you need like a big river here to keep filling up the reservoir, and there are only a limited number of places in the world that have rivers with enough water flow to really keep this up. So Niagara Falls has a huge river that runs into it, and other limited number of places it works well, but it doesn't really scale to solve the problems around the planet. So what to do? Well, one simple yet clever approach to dealing with these limitations is an idea that is known as pumped hydro. And it's basically like a hydroelectric plant, except instead of relying on a reservoir that is fed by a river, you just have a lake of some sort. It doesn't have to have a water source, a big flow into it. And the lake has to be located up high. And then at some lower elevation, you locate your electrical generators. And just like in a conventional hydroelectric plant, you have water flowing down from an elevation, picking up kinetic energy as the gravitational potential energy of the water decreases. And by the time the water gets to the bottom, it's moving fast, and it can run electrical generators and generate power. But the twist is that you also have in the same establishment, you have pumps that are run by electricity that are capable of pumping the water back uphill. So the idea is that the electricity is supplied by some green energy source, solar or wind, and maybe the solar panels are really located right nearby if it's a sunny place, or maybe they're some distance away. But in any event, electricity can flow in both directions here. When it's time to make electricity, you let water flow from the upper reservoir down, run the generators, and the electricity flows this way. But then, if you have an excess of electricity, it's a very sunny or windy day, and you have excess, you can use some of that electricity to run motors, which can pump the water back uphill into the upper reservoir. So that is pretty clever to have a self-contained system that can both store energy in the form of gravitational potential energy, and then when you need it, use that stored energy to make electricity. And this is an idea that is sort of played out locally. I confess I didn't know about this until I read about it in the Wolfson textbook. If you look in chapter 7 of Wolfson, there's a little sidebar about a pumped hydro storage, and it mentions this place called the Northfield Mountain Pump Storage Project. And if you look it up on the map, Northfield Mountain is in Massachusetts, according to Google Maps. It's something like an hour and 34 minutes from Wellesley, Massachusetts. It's in the northwestern part of Massachusetts, not far from the Vermont border. And let's look at some numbers. Here's a picture of what the upper reservoir looks like at Northfield Mountain Pump Storage. And let's do some numbers. And by doing the numbers that are sort of alluded to in this problem, you can get some sense of the both the promise and the limitations of such an approach to providing backup storage to solve the intermittency problem of sustainable energy sources like solar and wind. Okay, so we're told in the problem that the total mass of water in this upper reservoir is something like 2 times 10 to the 10th kilograms of water, which is an awful lot of water, it sounds like. So the mass that we are dealing with is 2 times 10 to the 10th kilograms. And the height of the upper reservoir above the lower reservoir is, I'm going to round off to 200 meters. It's 214 meters, but let's call it an even 200 meters. And that means that the gravitational potential energy stored in the upper reservoir is just, of course, mgh. And plugging in the numbers, that's 2 times 10 to the 10th kilograms. That's called G 10 meters per second squared times 200 meters is the height. And if you multiply all those numbers together, you get the gravitational potential energy is roughly 4 times 10 to the 13th, and the units are, of course, joules. Now, that sounds like an enormous number of joules, but before you celebrate, let's think about typical energy use. So here's a rule of thumb. A typical single-family house, at least in a place like Wellesley, houses use energy. So a typical house uses energy at a rate of about 10 to the fourth joules per second, or 10 kilowatts, is the rate at which a typical single family house is consuming electrical energy. And the town of Wellesley has, let's say, on the order of 10 to the fourth houses. That's probably a little high, but this is just an order of magnitude calculation. So that means just the town of Wellesley uses 10 to the eighth joules of electricity per second, or that is 100 megawatts, is the rate at which our town consumes electrical energy. So that's a lot of joules every second. And there are on the order of 10 to the fifth seconds in a day. So we're talking about a reservoir like the one at Northfield Mountain, um, can store, if we're just powering the town of Wellesley, it might be able to store 4 days worth of electricity. So if we were relying on solar and wind to provide our energy, and it got very dark and still, and there wasn't much sunlight or wind for a stretch of a few days, just this one facility and just the town of Wellesley wouldn't really be sufficient to solve the intermittency problem. And then if you think Wellesley is just one town out of many in Massachusetts, you realize that uh, if this idea of pumped hydro is really going to make a difference, you're gonna have to build lots of these all over the place, or make them much bigger than this one is, in order to really make a dent in the problem. And if you really want to understand sort of the limitation with the hydroelectric solutions, you really want to focus on this concept of energy density. And what we mean by energy density is the amount of energy, either per unit mass, that's one type of energy density, or another type of energy density is an amount of energy stored per volume. So here's a chart that shows different ways of storing energy, and it's giving the energy density either in terms of the amount of energy stored per volume, liter, L stands for liter, that's energy per volume, or the horizontal axis is giving what the energy density would be per kilogram of mass. So if you look at something like gasoline here, gasoline stores 35 if you look, let's do it in terms of energy per mass. So something like the kind of gasoline you put in your car has close to 50 megajoules of energy for every kilogram of gasoline that you have, 50 megajoules. And if you think back to the Northfield Mountain Pump Storage Facility, there, every time we raised a kilogram of water 200 meters in the air, the energy in that case, mgh, if m is 1 kilogram and g is 10 meters per second squared and h is 200 meters, that's just 2,000 joules per kilogram of water in the reservoir. And what you see is that that's 2 kilojoules as opposed to 40 megajoules for gasoline. So the energy density in something like a fossil fuel is just, more than uh, 3 orders of magnitude greater than it is for water. So really, there's a lot of attraction in finding energy storage solutions that are going to have greater energy density than you get from taking advantage of the gravitational potential energy of something like water. So that's why fossil fuels are so popular, is because they have such high energy densities and we can carry them around in our cars. Uh, Batteries, if you want to power an electric car, they at least show up on this scale. They have energy densities at least on the order of megajoules per kilogram, much less than gasoline, which is a disadvantage for electric cars, but still a lot greater than trying to store all your energy in the form of gravitational potential energy. So anyway, that gives you an idea of some of the ways in which the ideas that we're developing about energy for Physics 107 end up forming the basis for discussion for how you deal with real world energy problems. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.